Welcome to session 2, where we're going to explore the interaction of magnets, what magnetic fields kind of look like, and a little bit about the Earth's magnetic field. I want to start by sprinkling these steel filings onto this sheet of white paper. The filings are very dark, so we get a good contrast. We're about there, a little bit more. Now, although these filings are in the Earth's magnetic field, the Earth's magnetic field is not very intense. It's very large, very important to life on Earth, but it's just not strong enough to overcome the friction of these particles. In fact, I'm going to tap on the table. Here you can look at it from over the top, and I'm sure you don't see a pattern either. I'm going to tap on the table here. If the Earth's field was really strong, we might see some little lines here. The reason you see a line here is because my paper is grooved. Okay? So, if we want to see a pattern of a magnetic field, we need a stronger field. So I'm going to place this piece of plastic on here so that the magnets don't grab all the particles, and then I have to take them off. So let's set this down here like that, and let's tap the table again. And now we've got a pretty nice magnetic field. Now, the magnetic field isn't just in that plane. It's a three-dimensional magnetic field, not just a two-dimensional magnetic field. And I can show you that with this little device here. There's a little magnet on this propeller. And as I move this along, you can see it responding to the magnetic field that's up here. Okay. Now, this is a great way to see what a magnetic field looks like, but it's not a very practical way of looking for weak magnetic fields. These little particles wouldn't even detect the Earth's magnetic field. Now, maybe if they were floating in a liquid, we might have been able to do something, but with this configuration, it's not working. Now, a simple compass is really very sensitive. So here you can see that it's pointing toward me, which is the direction, is the northern direction. Not only does it detect the Earth's magnetic field, it will respond to this magnet way over here, which is fractions of the Earth's magnetic field. Okay, so very sensitive. And let's take it down here and notice how it lines up with the magnetic lines of force. It's parallel to the magnetic field that we've created with the U-shaped magnets. No matter where I put it, it lines up with that magnetic field. Okay. All right, let's take this off and move this out of the way. Now, one of the things you'll notice about my magnets is they have their poles color-coded. North poles are all red, south poles are blue, and the reason I did that is because I have a whole bunch of compasses that you're going to see later that have red north poles. So to be consistent, all of my magnets have their north poles marked with red and their south poles with blue. Now, I have a question for you. It's a simple answer. Why do we call the North Pole of a magnet the North Pole? Simple answer, not a trick question. And you probably guessed. So if I hung this from a string and waited long enough, the end that points to the North Geographic Pole is the one we call the North Pole. It's as simple as that. Okay? Now, having played with magnets or studied them, you know that south repels south is attracted to north. North repels north and is attracted to south. So the one we call the North Magnetic Pole wants to point to a South Magnetic Pole. And since it wants to point, here's a globe in your imagination. Since it wants to point to the North Geographic Pole, what's the polarity up there at the Arctic? What's the polarity? It must be a south pole. That's why a north pole of a magnet wants to point up there. Okay? So I've marked this with blue for the south magnetic pole. And I've marked this with red for a north magnetic pole. Now the axis of rotation and the axis of the magnetic poles do not line up. They're at an angle with each other. Currently, I think that the pole up here, the south pole, south magnetic pole, is somewhere in far northern Canada. Now, that lining up of the poles, the north and the south, have flipped thousands and thousands of times over the lifetime of the Earth. So let's take a look at the magnetic field around the Earth. So we'll put this right there, right there. Now, I always do that. I put Santa in the South Pole and the penguins in the North Pole. That was not good. All right. So I put Santa here so you don't get confused. This S is the magnetic pole, not the geographic pole. So if you'll look at the lines of force, you'll see that I've got arrows on the lines of force, and they're going in this direction from a north magnetic pole to a south magnetic pole. Magnetic fields are vectors. Electric and magnetic fields are vectors. What's that mean? Well, they have not only magnitude, how strong they are, but which way they're pointing. It's important which way they're pointing when we're trying to do physics problems or engineering problems. So, the direction of the magnetic field is from a north magnetic pole to a south magnetic pole, whether it's the Earth or a magnet. So the magnetic field goes from a north magnetic pole to a south magnetic pole. That's the direction. Now, for your purposes, what's important about that is that that arrow is the direction that let me turn this so you can see the color, that the North Pole would be pushed. So North Poles would be pushed in the direction of the arrows, South Poles would be pushed in the opposite direction of the arrows. What that means is, if I've got this sitting here like this and all of a sudden it turns, so the North Pole is pointing that way, someone must have turned on a strong magnetic field that affected the magnet. Well, in our next session, we are going to explore the relationship between electricity and magnetism, how one produces the other, and hope to see you then.